Dear all, welcome to the GATE class. Today, my name is K.S.MARGARET, Assistant Professor, Triple E Department from SA Engineering College. Today I am going to discuss about the three-phase induction machine and the torque speed characteristics of these three-phase induction machines. So before going into the GATE questions, let us discuss the basic formulas and the characteristics of the torque speed characteristics of induction machine. So this is the basic characteristics of your torque and speed of an induction motor. So you can see the x-axis is your speed and your y-axis is your torque, and we have got different types of torque. First one is your locked rotor torque, which is nothing but your standstill torque, otherwise called as your starting torque. And you can see the maximum torque T is given is nothing but your full load torque, and which operates the speed of N, that is nothing but your rotor speed, and Ns indicates the synchronous speed. So locked rotor torque is always 1 times the full load torque, and maximum torque is 2.5 times the full load torque. So there is another torque called pull-up torque. So they will always, initially the torque will be 1.5 times the full load torque, and it gets reduced and then it increases to the maximum value. So the pull load torque, which tries to pull the load, so based on that it reduces and increases, and that is called as your pull-up torque. And you can see that motor actually tries to run in the synchronous speed, but it never reaches the NS. There is always a slip between your rotor speed and your rotor synchronous speed. So that is why slip is the main factor to be considered while studying the induction motor and torque speed characteristics. So this is the typical torque speed curve with two different loads. You can see this is a typical curve we saw in the first slide, and I have got two loads. One is load A, the other one is load B. And you can see these two loads intersect at one common point. So the intersection of these two characteristics actually gives you the operating torque and the speed of the motor. So the point where both the loads A and B intersects is called as the operating characteristics of the motor. Now we will see the torque equation. Generally, torque equation of a three-phase induction motor is given by K into S into R2 E2 naught square by R2 square plus S X2 naught square. That is, K is a constant which is given by 3 by 2 pi ns, which is nothing but your angular speed, and R2 is your rotor resistance secondary side, and E2 is your rotor EMF in the secondary side, otherwise rotor EMF, and X2 naught is your rotor reactance. Okay, so this is the overall formula for your torque. But at starting condition, as I said, it is a standstill. Your motor is standstill, so slip value will be equal to 1. So when S equal to 1, your torque formula will be KR2 E2 naught square by R2 square by X2 naught square. But at maximum torque, the condition R2 is equal to X2 naught Xs. Actually, the rotor resistance will be equal to S times your reactance value. So while substituting this in this formula, you can see the torque value will become K E2 naught square by 2 X2 naught. So that means the formula of your maximum torque is equal to, it depends upon your rotor EMF and your reactance, but not the resistance. But if you see the speed during the maximum torque, speed formula is generally given by Nm, nothing but indicates the motor speed, otherwise you can say it as a rotor speed also, is equal to Ns into 1 minus Sm. So Ns is your synchronous speed, S is your slip. So maximum torque, we saw that K E2 square by 2 X2 naught. So and the condition for maximum torque is R2 is equal to X 2 times S into X2 naught. So S is equal to R2 by X2 naught. So you can see that in this particular equation, the torque doesn't depends upon the resistance, but the condition for the maximum torque itself, R2 is equal to S times your X2 naught, with nothing but S is equal to R2 by X2 naught. So your S depends upon your resistance as well as your reactance. So when there is some change in your slip, the resistance value will also change. So resistance has a great effect in changing the torque. So from this equation, even though your torque is independent of your rotor resistance, based on the resistance value, the maximum torque remains the same, but the point at which it reaches the maximum torque will vary based on the resistance value. Whether it is the resistance value smaller or greater, based on that, the point at which it reaches the maximum torque will be different, but the torque remains the same for all things. And based on that, the slope of the curve will also become sharper. Slope of this curve for torque speed will also become sharper. So you can see this graph. You can see this is your maximum torque. It remains the same for all different resistance. First one is your resistance with high value, and second is your resistance with your medium value, and third one is your resistance with your low value. So you can see all the points reaches the maximum torque. The maximum torque value remains the same, but because of the values changes in your resistance, lower the value of resistance, the slope value changes. Okay, so as well as I have already told you about the pull-out torque. So when the resistance is more, the pull-out torque becomes less. When the resistance keeps on decreasing, your pull-out torque also increases. So now let us discuss some gate questions. This is the first question. The slip of an induction motor normally does not depend on rotor speed, synchronous speed, shaft torque, core loss components. So we all know that the formula for the slip is Ns minus Nr by Ns, where Ns is your synchronous speed, Nr is your rotor speed. So from this equation itself, we can say that your slip obviously depends upon your synchronous speed, which is your B option. It also depends upon your rotor speed, which is your A option. So first two option is not the answer. When you take the third point, shaft torque, yes, it actually depends upon the shaft torque also, but we should know the reason behind it. So let's see the explanation. As I said already, let us take this is the nominal or behavior of your induction motor torque speed characteristics. So let us assume this R value somewhere around medium or large, and you can see this is your speed and torque. There is a point called load torque, or otherwise let us take this point TL as a steady state point where your electromagnetic torque is equal to your load torque. So the condition where your electromagnetic torque is equal to your load torque is called as your steady state point. So let us assume the respective or corresponding speed at steady state point is Nr, which is your rotor speed. So as said earlier, your rotor never reaches your synchronous speed. It will try to catch up the speed, but there is always a difference between your Ns speed and Nr. Okay, so now suddenly there is a disturbance in the load. Okay, so because of that, what happens? Your steady state point has been changed to some other point. That means your electromagnetic torque is not equal. It has been changed to some other point. So there is a change in your load torque. So when your load torque changes, automatically the respective speed gets also varies. So your speed is also varied. So it has been reduced from the previous one. So based on this, you can say that when your TL changes, that is load torque changes, there is a change in your rotor speed also. So since rotor speed changes, we know that in the slip formula we have the rotor speed also. So because of the shaft torque, rotor torque, which depends upon the shaft again, the changes in the speed takes place. The rotor speed changes, which also affects your slips. So based on this explanation, we can say that shaft torque also depends on the slip of an induction motor, and finally the core loss components will not depend on the slip value, because slip of induction motor will not depend upon the core loss component, because it only depends upon the iron loss of core losses and the current that flows in the core of your induction motor. So the answer is obviously your core loss component. We will see one more question. The torque speed characteristics of motor and load for two cases are shown in the figure. So Tm indicates your motor torque and TL indicates your load torque. So two diagrams are shown here. The load torque is equal to motor torque at points P, Q, R and S. So that means all these are steady points. P is one steady point, Q is one steady point in this place, and here R and S is the points they have given where your motor torque and load torque both are equal. So what is asked in the question is we have to find at which point the system is stable. That is the question actually. Torque speed is given, we have to find out at which point it is stable. So first graph will take the answer I have already given. We'll see the explanation now. So let us take this graph. So this is the first graph. We can say that x-axis is your torque and y-axis is your speed. So if you see this quadrant, your torque is in positive axis and similarly your speed is in your negative axis. So one force is torque is positive and speed is negative. So both are opposing force. First we have to analyze at which quadrant both the speed and torque lies. So from this itself we can say that torque is positive and speed is in the opposite or negative direction. Okay, so any case, any operating point, if you want to discuss the stability of the system, you need to find out two things. One is which one is a supporting force and which one is the opposing force. So since torque has got a positive value and speed is a negative value, always speed depends upon the motor and your TL, if you take this point, stability point Q. Okay, so now in this Q, it is a steady state point. You can see that at this point, let us assume the speed is N1. Okay, and this point, suppose to find the stability of a system, we have to give a disturbance. You have to give a disturbance the speed such that your speed can be increased or your speed can be decreased. So now let us take, we are going to decrease the speed from N1 to N1 point. So N1 dash. So what happens? This curve, actually this blue curve resembles your motor torque and the straight line resembles your load torque. So when you reduce the speed, what happens? Your motor torque is in a different point and your load torque is in your different point. So when you compare these 2 points, which one is greater? We can say that your load torque, magnitude of load torque is greater than your motor torque. So here actually your load torque acts as a supporting factor because it is in the positive axis. Your torque is in the positive axis. Motor torque, because of shaft only your motor runs, so therefore speed contributes more to the shaft and therefore motor torque is in the negative value, so it is the opposing force. So since the supporting force is greater than your opposing force, so what happens? The supporting force will try to support and therefore it will try to run in the same speed. So it will be try to run in the same speed N1 dash, but it will not try to move to N1. So that means your speed will be keep on accelerating only. It will not reach the previous value. So your Q value is not a stable point because your speed keeps on changing whenever there is a disturbance. So Q is a unstable point. But when you take the point P, okay, so you can say again P is a stable point. Let us assume N2 is the speed for respect to the point P. Now again I am going to give a disturbance in the speed such that again I am going to decrease the speed to N2 dash. So what happens? Here TL is the respective load torque and TM is the respective motor torque. Now if you see the magnitude of these two components, you can say that TM, that is motor torque, is greater than your load torque. So motor torque is greater than your load torque. We have already seen that motor torque is the opposing force and supporting force is load torque. So since motor torque, your speed is a opposing force which is greater, it tried to decelerate and it tried to go to this original position. So because of deceleration of your speed, it tries to reach the N2. So there is a possibility it will act oppositely and it will try to bring the speed back to N2. So therefore from this concept we can say the point P is the stable operating region. Okay, so similarly this next slide, next diagram, if you see, this is again we have to check for the quadrant. So this is torque and this is your speed. Actually it is in your first quadrant. This is a positive axis. I mean both your torque is positive, and you can see here this R point and S point are the 2 points they have given where you have the steady state points. Let us first take for the R point. Let us assume the speed at R point is N1. Here both the values are actually equal, I mean positive. So here let us assume the value of speed at R point is N1. Now I am going to give a disturbance. I am going to increase the speed from N1 to N1 dash. I am going to increase this, and because of that what have we get 2 points. One is load torque, the other one is motor torque. Now if you compare the magnitude of both the torques, your motor torque magnitude is greater than your load torque. Your motor torque is greater than your load torque, and since your motor torque here it is a supporting torque and this is your opposing torque. Load torque is your opposing torque. So magnitude of Tm is greater, so your supporting torque tries to overcome the load torque. So because of that it will keep on increasing the speed and it will not come back to your original point. So therefore R is not a stable point. But when you go for the S point, let us assume the speed at S point steady state is N2. Now again I am going to give a disturbance. I am going to increase the speed to N2 dash. So now you can see it reaches your Tm value somewhere at this point, and TL it keeps on increasing. We can't even see the value. So obviously TL value is greater than Tm value. Okay, so TL again here it is a opposing force which is with the magnitude of which is very great. So it tries to bring back the speed to its original position, because being an opposing force, the more force will be acting on that, because the magnitude is also very high. It tries to bring back the speed to the original speed N2. So here the point S is called as a stable point because it makes the speed, it tries to pull the speed to its original position. So S is called as your stable region. So we can see that from this both the equation, actually this is the axis I should have drawn. This speed is your positive, torque is also positive. Both are positive case in this case. So we discuss, as per the discussion we saw in the first one, what is the stable point? T is the stable point, because even though when you give disturbance, the speed is try to overcome and come to the original speed again. And here also when you compare R and S, S is a stable point because it tries to pull the speed to its original because of the higher magnitude and higher opposing force. So this is the answer for these two questions. So hope you would have understand this topic, and we'll see some more questions and we'll discuss some more topics in the next video. Thank you all.